So our next mosquito mapper group was working on a statistical analysis to determine infection rate of mosquito-borne diseases in Uganda, USA, and India.
We aim to use statistical analysis to determine the infection rate of mosquito-borne diseases in Uganda, the USA, and India. Mosquito-borne diseases have been known to cause an increasing risk on local human populations. As global temperatures rise, the mosquito-borne diseases pose an ever-increasing threat to local human populations and developing countries across the globe. So it is important for all of us to be proactive in the prevention of mosquito-borne diseases and to better be able to predict when a mosquito-borne outbreak will occur.
The mathematical model that we came up with used infection rate data for chikungunya and malaria. India and Uganda are known to have high rates of chikungunya and malaria, whereas the US has low levels of these diseases. And the US plays an important factor as it acts as a validation for our mathematical model.
The purpose of our research is to create a mathematical model that can estimate the likelihood of mosquito-borne diseases outbreaks that affect local populations using pre-existing data and a chi-square test. We hypothesized that it is possible to predict the likelihood of a mosquito outbreak by analyzing environmental factors such as pH, average temperature, and the color magnitude of our region by developing an equation that can estimate the infection rate over a given period of time.
The three images represent our vectors used in our code for our three independent variables, which we use to output our disease infection rate.
As for the materials, we used Google Sheets, a JavaScript compiler, a code that helped us analyze images of a given environment, data of variables and infection rates, land cover observations, and mathematical software.
We computed a color average using the code by stacking color vectors on top of each other to determine the average color in a region known to harbor mosquitoes.
By stacking these color vectors, we were able to find an average which we used for our USA data analysis and the values on the screen.
An important part of our project was the usage of Cobb-Douglas function, and this represents the relationship between two or more inputs, in this case pH, average temperature, and magnitude of color average, and the number of outputs that can be produced, which is our infection rate.
The following is the code that we use for the Cobb-Douglas function. As you can see, in variable A, we have a list of data that has been compiled for regions all throughout these three countries. The first value indicates the pH level, then we have the average temperature in a region, then we have the other values, including the temperature and the magnitude of the color average. Variable B aims to establish a relationship between all of these data variables, and we use the next parts of the code in order to figure out whether or not there exists a plane which interjects all of these data points. This is a picture of the relationship that we established. The plane that interjects all of these data points has been shown to establish a relationship between all the independent variables and the one dependent variable that we have.
For a chi-squared test, we determined a value of 2.29. Because this was less than our critical value at p equals 0.05, we rejected our alternative hypothesis. This means that we found there to be some sort of relationship between the independent variables and the dependent variable.
The chi-squared tests produced results that were statistically significant. We used a p-value of 0.05, and that was included in a confidence interval of 95%. Because our calculated chi-squared value was less than the p-value at 0.05, we were 95% confident that the results that we obtained for the infection rate in our region was representative of the true relationship with nature.
To conclude, while the results of the mathematical analysis did not output a single equation, we were able to make a mathematical model with a clear correlation with the infection rates in the areas we looked at. The rejection of the alternative hypothesis indicates that we were able to demonstrate a relationship between our chosen independent variables and our output variable.
In the future, something we could do is analyze the relationship between color vector and other climate-related variables, and also use machine learning in order to better our model.
These are our highlights and reflections upon finishing this internship. Thank you so much.
Thank you.
Thank you.
Thank you.
I think we have a few members of the team that are with us. So have you used mathematical models in any new projects since last summer?
Yes, certainly. In fact, one of the new projects that we're working on right now is determining exoplanets, and often determining where exoplanets are relative to our position on Earth requires extensive use of statistical analysis, often using chi-squared tests and Bayesian statistical models. So a lot of the stuff that we actually used in the SEAS project that we worked on over the summer can be easily mapped to at least my project that I conducted on exoplanetology.
What do you feel was your biggest challenge in conducting your research last summer?
Yeah, I can start us off with that. So I think one of the biggest challenges we faced was obviously having this experience be virtual. And because our team was quite large, we had over 7 members and we were all in different time zones. I'm in California. 5 of us were in Texas, and then there was another one from Florida. So finding times to meet up and having that communication was definitely quite a challenge. But I think in the end, this challenge ultimately served us quite well because it really compelled us to strengthen our leadership skills and to really push us to be openly communicative of our ideas and be decisive about ideas when it was the time to be. So overall, I think communication and finding times to meet up was the biggest challenge, but ultimately it served us quite well in the end.
So after your SEAS internship, has your view on what you plan to major in college changed, or did it solidify what you already had an interest in?
I would certainly say that it strengthened my understanding of the field that I want to go into. I want to become an astrophysicist, and I also want to major in computer science. And really having the ability to take a deep dive into all of these different computer science, statistical, and mathematical methods that we use throughout this project really opened my eyes to the possibility of applying all the knowledge that we learn in school and elsewhere to real tangible projects. And I think that when I go off to college and conduct research and ultimately get my PhD, I'll be able to use all of these concepts together and create a really solid foundation in the subjects that I want to learn the most.
Yeah, and for me, I think it's only solidified what I want to study. When I go to college this fall, I really want to study physics. And a lot of physics is comprised of research. And prior to this experience, I didn't have much experience with conducting research projects. And after this experience, I've just realized just how intersectional the ideas and methods of science are in other aspects of, physics and other aspects of science. So I think this experience has only solidified what I want to study, and it's just assured the fact that a future as a scientist, as a physicist, is what I want for myself.
Well, congratulations to you both. It's obvious that you did an excellent job